What I'll talk about today is work on weak to strong generalization. I should say this is a joint work with the, where's my, I guess, okay. This is joint work with several co-authors, mostly Marco, who's sitting right here in the center. Marco actually did this work, so if you have any questions, then this is your guy later. And also with the Kaifeng, Dinglis, and Jeev and Shriyan. Okay, so I'm actually curious, how many people heard of weak to strong generalization, just as a buzzword? Okay. So what is weak to strong generalization? So the basic question we're asking here, the question of weak to strong generalization is as follows. We have a weak teacher and a strong student. And the weak teacher learns directly by observing the world, right? So I mean, you look and you get training data directly from the world, and learns by kind of optimizing, minimizing the loss on the truth. And then the student is much smarter than the teacher, has maybe a much bigger brain, but they never get to see the world directly. They only get training signal from the teacher. So they only kind of get the labels generated by the teacher. Okay? And so their training objective is just matching the teacher labels. Okay? And the question is whether a student that can only learn from their teacher, whether they can be better than the teacher. Okay? So what do we mean by better here? Of course, by better, we mean better on the real world. Okay, so can a student have a smaller error with respect to the real world, even though they never observed it, and they only observed it with this teacher who's maybe not so good? Okay? Is the basic question clear? Okay, great. Okay, so this question received a lot of attention recently due to this very influential paper by OpenAI. And OpenAI, really, their motivation to starting this is they're concerned that at some point the computers will be better than us, but the computers can only learn from us. So this is kind of let me use my stick. Based on the OpenAI view of the world, this is where we are now. We're teaching a computer that's still maybe not quite as, okay, maybe I should say this is from 3 years ago. They're probably also thinking things changed since then, but very soon, maybe already now, we're in this situation where we're teaching a computer that's much, much stronger than us. So can we do that? I mean, can we actually teach a computer that's stronger than us? And then they said, as an analogy, let's study a weak computer teaching a stronger computer. Okay, so I did this experiment. In particular, their weak student was a GPT-2 model, and their strong student was a GPT-3 model. So they took a pre-trained GPT-2 and a pre-trained GPT-3. They taught that pre-trained GPT-2 several classification problems, and then took that, did I say 3? I guess the GPT-2 and GPT-4. And then they used the GPT-2 generated labels to teach a GPT-4 model. And what they observed, lo and behold, is that the GPT-4 model that was only trained through GPT-2 was better than the GPT-2 teacher. Okay? So they see here, so they said, wow, we observe weak to strong generalization. How can this be? How can we have weak to strong generalization? Let's try to explain it. So first of all, I want to point out that so this is a paper from 2023, but actually weak to strong generalization goes back to 1959 and the first ever paper written about machine learning. So this is a paper that I think the first time the word machine learning appeared in print. And this is a paper by Arthur Summers teaching the computer to play checkers. And already in the abstract for this paper, Arthur Summers points out that the student, the computer, was better at playing checkers than the teachers that taught it. Okay? So this idea of having a teacher that's better than the student is not new at all, even in the context of computers. And really, I think maybe this is maybe not surprising us at all. Then the checkers computers can be better than its teacher, and really maybe to understand what's going on here, and why this is not at all surprising, we should think of several ways in which like a teacher can be better than a student can be better than its teacher. Okay? So there are many mechanisms for this, and one mechanism, which is maybe also what's going on with the checkers. Is that if the student has much more test time compute, can do much more search, then of course it can be better than the teacher, right? So I can, if I were to teach a very smart, really smart kid how to play chess. I'm not a very good chess player, so the bar here doesn't have to be very high. Okay, I'm sure many of your kids, if I explain how to play chess, then they can beat me. And the way they'll beat me is because they'll just do a search better, right? I mean, they'll be able to figure out certain winning strategies like search deeper or something like that, okay? And so that's an obvious way in which the computer can be better, and we already see that happening. Another way that's related to that is through self-play. So once once the computer can kind of do search, not only can they do search at inference time, but they can also do that to train themselves, right? So if I teach a kid how to play chess, then the kid can play chess against itself or like figure it out, and gradually, just from playing against itself, figure out, like learn winning strategies, okay? And kind of train itself and also be better, okay? So in both of these cases, it's kind of clear how a student can be better than the teacher. And I would argue that in both of these cases, what's kind of uniting them is these work in settings in which verification is easy, right? So it's easy to check whether I won or not. Okay, that requires some teaching, but like as long as the teacher is good enough to teach the student what does it mean to win, okay, like what it can teach to validate. If the search problem is much harder than the verification problem, there's this gap that we're well aware of and look at it in computer science. Then there's huge advantage to compute, right? We can either compute at test time or compute through self-play. Okay, but so here in this cases we can easily the student can easily beat the teacher, and this is maybe also what happens in Arthur Samuels, and this is maybe not what happened in with the GPT-4 versus GPT-2, but then there's another way in which it's kind of obvious that the student can beat the teacher, and this is if the student just has better knowledge than the teacher. Either the student is kind of built in with better inductive bias, or the student obtained this through some pre-training. Okay? So for example, my co-author Zhuyan Li, he has different pre-training than me. He was pre-trained on Chinese. I was not pre-trained on Chinese. Okay? He's also much smarter than me. But the thing is that if I teach Zhuyan how to pronounce the name of the Chinese students in my class, okay, very quickly, Zhuyan as a student here would be much better than me. And the reason he's going to be much better than me is not because he's smarter. Okay? I mean, he's also smarter, but this has nothing to do with it, right? The reason he's going to be better is he's pre-trained on Chinese. And from me trying to like mispronounce the Chinese names very noisily, with Zhuyan's excellent prior knowledge of how Chinese names should sound, he can figure out how to pronounce them correctly and quickly be able to do it, and be able to be better than me in this. Okay, so that's clear, I think. Okay, and so here what we're seeing is that where this is okay. So what we're seeing is another way, and this is kind of maybe what happened in GPT-2. I think maybe better captures what happened in GPT-2 versus GPT-4 experiments, because the GPT-4 model not only is a bigger model, but also pre-trained on a lot more data. Okay? And so in particular, if the tasks that were programmed were already things that GPT-4 kind of already saw during training, then it's not surprising that it'll be better at it. Okay? And so this is another way in which we can have weak to strong generalization. And all these ways are ways that I feel are, I wouldn't, maybe kind of boring, right? They're not really what, our goal here. There's a way that's easy to understand. But when studying weak to strong generalization, I think it's important to distinguish between these different mechanisms for weak to strong generalization and make sure that what we're studying really is weak to strong generalization just because the student is somehow stronger or smarter or has a bigger brain, okay? And this is really, I think, what we want to try to get to, and what I'm going to get to in this talk, and try to focus on weak to strong generalization only thanks to the fact that the teacher is just bigger than the student. So I keep saying this the other way around, right? I mean, I hope I'm not. The student is bigger than the teacher, right? Just based on the fact the student has, a bigger brain, more units, bigger model, okay, more parameters than the teacher. In that case, can we have weak to strong generalization? Okay, so let's go back to here, right? So what we want is we want to take a small teacher with a small number of units, small number of neurons, small number of parameters, and a big student, and without any pre-training or additional data, right? So the student doesn't have this advantage that it was pre-trained and has better inductive bias specific for the domain. And there's also no test time compute here, no search. Okay? We're going to train the teacher on reality, train the student on the teacher, and we're going to see whether the student can beat the teacher. So this is exactly what we're going to do. And specifically what we're going to do is we're going to take a two-layer neural network. But as the title probably already hinted to you, I'm training the student. Did I? No. Okay. This is not my training objective. This is what I'm running there is what I'm comparing. So I'm training the student on the teacher, and then I'm measuring the student's performance on reality. So these are the two quantities I'm going to compare. Okay, is that clear? Okay, excellent. Okay, so the model we're going to use is a two-layer neural net. But as you probably guessed from the title, we're going to set the bottom layer to be fixed and random, and only train the top layer. Okay? So depending on how you want to think about it, this is just a random feature model or a two-layer neural network with a random bottom layer. Okay? Same thing. So this is the model we're going to look at. So again, what's going on here? We have a random feature model with a small number of random features for the teacher, large number of random features for the students, same distributions over features. Okay? We're going to first of all draw these random features, again from the same distribution, just more features for the student. We're going to train the teacher on reality, and the teacher here, not only are we going to train on reality, we're going to train it for infinite time on infinite data. So we're just going to train it to minimize the loss versus the population. Okay? And then we're going to train the teacher on the student. Okay? We're going to the student on the teacher. Sorry, we're going to train the student. We're going to train the student on the teacher. So that means, and the way we're going to do that is we're going to train it by gradient flow on this loss. So now, sorry, this is not a pointer. Gradient flow on the loss, which is now the loss versus the teacher. Okay, so this is the training signal. Okay, now very importantly, we're going to train with gradient flow, but we're going to train with early stop gradient flow. So if we train with gradient flow without early stopping, we're going to fully minimize this objective. Right? This is a convex problem. And the thing is that since the student in some sense subsumes the teacher, okay, can do anything the teacher can, then if we're going to really train to zero error, the student is just going to imitate the teacher. So it's going to imitate also all the teacher mistakes. Okay? And so it's important to actually not let the student fully imitate the teacher. And then we're going to achieve that through early stopping. And this is also matches the Burns et al. Experiments, the OpenAI experiments. They also observed that early stopping is necessary. And they asked, like, how come we need early stopping? Why is the role of early stopping here? Okay, so first of all, it's clear that without early stopping, this is not going to work. Again, GPT-4 can completely imitate GPT-2 if you just let it, right? And so the early stopping here is essential. And what we're going to understand, what we're going to see is exactly how the early stopping comes in. Okay, and then say that here we take we're taking a gradient flow, taking the steps in here, and the other thing is, just for simplicity of analysis, we're also going to take the number of student units. So MS here is the size of the student. We're going to take this to infinity. So we're going to take an extreme case where the student is even smarter than Marco. It just has infinite brain size, like infinite number of features. The teacher is still limited. So the question is now, with a student which has infinite number of features, can it be better than the teacher that only has a finite number of features? Okay, we can make it all finite large enough, but for simplicity here, let's just take it to be infinite. Okay, just 1 second, and then we're going to compare the student loss on reality to the teacher loss on reality. Yes, Rene?
Should there be a minimum quality for the teacher?
Minimum quality?
If the teacher, at the end of the day, gives training examples that are all wrong.
Yeah, okay, so this is, I told you how the teacher is trained. As you if the teacher is trained this way, and the random features are like reasonable, then the teacher is not going to be all wrong. You're completely right that the question we're asking is it possible that are there settings in which the student can be better than the teacher? There are, of course, settings in which the student is not going to be better than the teacher. In particular, one case in which the student is going to be better than the teacher, if the teacher, as Rene said, is completely dumb and just is a zero in everything, right? I mean, just there's no labels, or all the labels are random, then the student is not going to be any better because the student's not going to know what to do with it, right? So of course there are settings in which the student is not going to be better than the teacher. What we're asking is, are the settings in which the students will be better than the teacher, and what are they? We're going to try to characterize, how can the student be better than the teacher? Is that clear? Okay, great. So you shouldn't be surprised if I'm presenting this talk, then the answer is yes, the student can be better than the teacher. Okay? So let's just see how much. Let me first of all tell you the results. So we show as follows. So let's first of all take a ReLU network. So we're going to take we take ReLU activations and take the data, the input distribution to just be spherical, and target at some low degree polynomial. It doesn't matter too much. Then in that case, what can we show is the student can in fact be better than the teacher. How much so? Well, it can be in some sense infinitely better than the teacher, in the sense that the ratio between the student error and the teacher error can be arbitrarily small, right? So the student could be 10 times better than the teacher, 100 times, any times better, right? In fact, this ratio goes to 0. And once the ratio goes to 0, we can ask, how much faster it goes to 0. And what we can prove is that the student can go to 0 about with the exponent of about 1.5. So the student error can be about the teacher error to the power of almost 1.5. Okay? And so this already shows that the student is going to be much, much better than the teacher, and particularly resolves the problem posed by Burns and all. They asked to analyze this. The way measured thing is this performance recovery gap, which is really, performance gap recovered, which is really just a different way of looking at this ratio, and saying this ratio is going to 0 is the same as saying that their performance recovery gap, which is kind of measured by how much does a teacher win, goes to 1. The student win goes to 1, which is the highest it can. Okay, so this is with ReLUs, but really what we see here is just saying that the ratio goes to 0 is not enough. The question is, what about this exponent? How far can we push this exponent? So this is with ReLU nets. We can push the exponent even more if we consider, instead of ReLU networks, just linear networks, but with a structured input distribution. So if we take just linear activations on the hidden units, and the input distribution, instead of being spherical, it follows, it has a structured covariance. It has a structured covariance with a few strong directions and the rest of the directions and a lot of weak directions. Okay? With the signal, of course, supported in strong directions. And in this case, we can show that the student can be quadratically better than the student. Okay? So the error decay for the student can be quadratically better. Okay? So much, much better. Okay, and we can see this also empirically. So for the ReLU case on the right-hand side, the experiments are much clearer. So first of all, on the bottom here, what we're plotting is the student error versus the teacher error, and we get a very nice quadratic fit there. And what we're seeing on the top is the effect of early stopping. So as I mentioned, all these results are with early stopping. So the more careful statement of the results is there exists a stopping time that will give me this benefit. Okay? And we see here, so this is the ratio to the student to the teacher squared, right? So we're claiming that this can be as low as 1. And we're seeing that we're getting here, this is the training time, that there's like a regime here in which the early stop, this is the regime where we're allowed to stop. So if we train for too little, the student has not yet learned. If we train for just right, which is this amount, then the student learned and is indeed performing better than the teacher. If we train too much, then the student is starting to replicate the teacher and is now not outperforming it. Okay? So this is for the linear case. In the ReLU case, we have a fit here. Our exponent of 1.5 is, this is just a bound. This is not the tightest possible bound. There are many reasons this is not tight. We don't know what the correct answer here. There's some experiments here that suggest it's something somewhat less than 2, 1.85. It also depends on exactly how you scale the dimensionality and the degree and other issues. We don't know how far we can push this exponent. I think for any of you who are interested in random feature models and can do better random metrics theory than we can, then I think this is an interesting mathematical question to try to figure out, just how far you can push this and what is the correct exponent here, because this is definitely not correct. I mean, it's correct as a bound, but it's definitely not tight. Yes, question. That's an excellent question. So the question here was, can the maybe I'll rephrase it the way I understood it. Can the student know when to stop learning? Can the student know when to figure out the stopping time without overfitting? Because the problem is that you might think, like usually when we talk about early stopping, we stop based on validation, right? So we can train, and then we can look at the validation error, and when the validation error starts increasing, then maybe we stop. Okay? But here, we can't stop based on validation because the student, the only thing they can validate on is the teacher. They don't like see the real world, okay? And so the error versus the teacher just gets better and better and better. So is there an internal way for the student to know when to stop without ever seeing the real labels? I don't know the answer to that. That's an excellent question. We provide, in some sense, I can tell you they don't even need that because we give you a theoretical time to stop. Right? I mean, so these guarantees come with a particular stopping time. Okay? So in theory, I can just tell you when to stop if you know, the problem setting. But this is not a very good answer. I mean, I think it is a good answer more practically, like what empirical criteria should I need in order to stop? And I don't have a good answer.
You can look at all of the neural network as a bunch of hyperparameters and sweep all of them.
I completely agree that this is important. I don't know, but Andrea maybe knows how to do it. Yeah. No, a different question? Yeah. So let's say that the student can request infinitely many samples. So this is not about number of samples. What we're analyzing is, let me just go to here, it's specified exactly here. The student learns by gradient flow on the loss versus the teacher with early stopping. So in order to do gradient flow, since you have to take an infinitesimal step size, you need infinitely many samples for any amount of gradient flow. We can turn this all, okay, I'm not sure if we should be able to. I don't think we actually did that. We, turn it into finite step size. I don't remember. You should be able to, instead of saying gradient flow, say small enough step size and get everything will be finite. But we're not like looking at the number of samples. We're assuming this is not something we're worried about. Does that answer? Yeah.
Just want to ask a clarification question. So for the linear network setting, signal only depends on finite number of coordinates.
Yes.
And MT is growing.
In what?
So MT, the number of neurons for teacher, is growing. Isn't that at some point the teacher should completely know beta? Will that be happening?
No, because
like for example, if k equal to 1.
No, because the dimensionality is also growing, right? So the teacher never. I mean, we'll see that actually in 2 slides. What's going on here? But the teacher, remember the teacher has random features. So it's not enough for the teachers to have k features. Even if the teacher has k features, those features are not aligned with the first k features. So the teacher will never have, for any number of features, the teacher is not going to have more than d features, right? So unless the feature has d features or very close to d features, it is not going to be aligned with the top D features. Right? If you take,
you just want to capture k of those.
But you have to take
a couple of them.
Sorry.
You only need the features from the top.
Right.
You only need to cover
top. You'll never get them, right? So if I take a subspace, if I take 2 random subspaces that are neither of them is the entire space, then you would never have one of them as a subset of the other, even if they're both very high dimension. Even if I take a one-dimensional space, in R100, I take a one-dimensional space in a 95-dimensional space. The one-dimensional space would not be a subspace of the random 95-dimensional space. You'll have some components outside. Does that answer your question? Okay, but we'll see it in a second. We'll see it exactly. Okay. So actually, last question before I go on. Yes.
Talking about the size of the student. Can you? But here, in the next slide, the accuracy that the student achieves is limited by the quality of the teacher.
Yeah, so I said the student is going to be quadratically better, or maybe a bit less than quadratically better than the teacher. It's not going to be, it's still limited by the teacher accuracy. It's just going to be better than it.
Yeah. But my point is, it doesn't depend on the
size of the teacher,
on the size of the student. Of the student. That's my point.
Right. So the theory that I presented here is for the theory as I presented here is for infinite-sized students. The experiments are for a finite-sized student, right? So the experiments in this regard, we're just taking some specific student size here. I I don't remember the student size. Marco, it's written here. Like the student is of size 16,000, which is close enough to infinity in the scale of these experiments, right? You're right that we would improve probably a bit if it increases, and we can also, as I said, even though I stated it here for infinite, you can easily make all this just for a large enough teacher and you get a large enough student, and you'll get another error term corresponding to the size of the student. It's going to vanish as the size of the student goes to infinity, which is not so interesting. So I'm not including it here. Okay. Okay. So let's try to answer the question there of what is actually happening here. Why is the student? In what way is the teacher not perfect, making errors, and how can the student be better than it? So let's look at the linear case. It's easier to understand. So in the linear case, the covariance of the data is structured in this way. There's a small number of strong components and many weak components. So what I'm showing you on the top here is the variance along each one of the components. You can think of it as coordinates if you prefer. Okay, so the variance along each one of the components. You have a few very high variance coordinates, a lot of like low variance coordinates. Okay, in the signal, okay, this is is a linear predictor. Right, because everything is linear here, that's supported only in the top ones, okay, with some coefficients that are not necessarily all equal. Okay, now let's first think of the teacher. So what happens for the teacher? The teacher fits optimally, but the problem is the teacher doesn't see this entire space. What the teacher sees is some random low-dimensional space that's maybe mostly skewed towards these high components, but not necessarily. Okay, and now what the teacher has to do is project this target, okay, into the space it sees. And exactly because what we said before, this three-dimensional space, if this teacher here is like, maybe 50-dimensional, as long as it's not full-dimensional, the space that it sees would never exactly span this three-dimensional space. And so in projecting to the teacher space, I get an approximation here. And this approximation means that both I'm not capturing these coordinates exactly, but I also have to have non-zero components in everything else. Right, because each of think of the basis directions or eigenvectors for the teacher, all of them have components also outside here. Right, so in order to change any of these components in the teacher, I have to also include other coordinates. Okay, this is just linear algebra. Okay, so the teacher would look something like this. And so I really you can think of kind of two sources of error here. One is that I didn't capture the signal exactly. And the second is that I have all these kind of additional components in the noise directions. Okay, the teacher, of course, doesn't know it because it's not that the teacher sees this composition, right? The teacher just sees its space. Okay, but now let's think of the student. So what is the student doing here? So the student is, again, we said everything here is a linear model. At the end of the day, the student learns the top features, but learns the top, but it's just learning some linear model beta. And the thing is that because the hidden units U are spherical, then the dynamics and the everything on W behaves the same as the dynamics on beta. Okay, especially number of features goes to infinity, then this U becomes effectively diagonal. Okay, and so and now, but what the teacher does is it does gradient flow. So this is the important thing to understand. What does gradient flow do? So we know exactly the behavior of gradient flow in the linear model. So what gradient flow would do is it learns all the components for all the components of beta, but with different speeds. So in particular, what we can show that if we write everything in the eigenspace of the teacher, of the student, the eigenspace of the learner, and the eigenspace of the student here is exactly the space that we see on the top here, because again the student sees infinite number of features, so its space matches exactly this the population space, okay, the feature population space. Then each component I is learned with a decay, and this is the first term here, with a speed that depends on the variance of that component. So the high variance components, the components that are where the covariance of the data is high, are learned quicker, right? This decays faster. And the components with low variance are learned much, much, much slower. Right? It takes me longer time to learn. And eventually, if t goes to infinity, all of these terms goes to 1, and I learned exactly beta. But in every finite time, I have a much better fit for the high variance component, which I learn quicker, than for the low variance components. Okay, so let's see how it works here. So what I'm learning is this purple thing, right? Because what I'm learning is not the reality, which is the green thing. I'm learning the teacher predictor. Okay? Okay, so I'm trying to match this purple thing, so I'm moving towards this purple thing. But on these components, I'm going to move the student, not me, Marco, is going to move very slowly towards the purple thing. And on the high variance component, it's going to move very quickly towards the purple thing. So if I stop it early, then here it barely moved towards the purple thing, barely left 0. But on the high variance component, it almost got there. Like it almost went almost all the way to the purple thing. And so that means that over here, I'm basically replicating on the signal directions. I'm replicating the teacher, and but on all the noise directions, I'm 0. I'm almost 0. Okay? And of course, this how much close to 0 I'm going to be here, and I'm going to match it here depends on the eigengap. I can make it as large as I want. Okay? And so what happens is the reason the teacher is winning, the student is winning, is it's not reducing the error here, right? The error that Marco is going to have here on the signal directions is just the same as my error. But where Marco is really winning is that it's winning on all these directions it can 0, right? So this is what gradient flow does. Note that if Marco, instead of using gradient flow, Marco could have also done this more directly by saying, aha, I know this is the covariance structure. I know there shouldn't be a signal here. I'm just going to 0 it out, okay? And just keep what's going on here. And this is actually exactly what gradient flow is doing, early stop gradient flow is doing. Okay, so now we just have to calculate exactly how much of the error is here versus here. And now we have to balance some things because, if there's not enough, and this maybe goes to René's question, if there's not enough alignment between the teacher space and the correct spectrum, then there's going to be too much error here, and I'm going to be bad, and Marco is also going to be bad, and he's not going to win. And if there's too much alignment, then there's not going to be any error here, and so it's not going to, he's not going to win because it's not going to be a big difference. So we have to balance exactly what maximizes the difference, and that's exactly the spectrum I showed you before, and we get this quadratic improvement. Okay? So this is the case in the linear case, and what's going on in the for ReLUs is exactly the same, except that now really you should think of all in the kernel space, right? Everything is eventually linear. I mean, all these problems are just linear problems in the top. The only difference is the ReLUs induce some kernel with some different eigenstructure, so you have to analyze the eigenstructure is now not as simple as this. You have to analyze the eigenstructure of the kernel induced by ReLUs, and then analyze what happens there. Okay, and I should say that the analysis here really has two parts. One is the deterministic part, which is in terms of the properties of the kernel, of the gap. So this is a very simple kernel, a simple covariance. So in terms of the properties of the actual student and teacher covariances and alignment between them, what would be the weak to strong generalization? And the second is the matrix random theory that tells us if we draw random features, how well would the student and the kernel teachers, the student kernel and the teacher kernel be aligned? Andrea?
Okay. I was wondering about the random matrix. Isn't this already studied in all possible details without any assumptions?
Maybe. I know, Marco, do you want to answer that? I mean, you're asking why we have gaps, why we couldn't figure it out completely?
Right.
So I think, okay, actually, Marco, do you want to answer this?
No, I want you to answer.
So no, I think that...
just kidding, Marco.
Yeah.
Nati can answer first, and then Marco can answer after Nati.
Double blind.
Okay, so the thing is that I think that part of the gap here is that what we're only basing ourselves on the gap in the spectrum. But if the spectrum is structured, then the analysis is just based on a single gap is too loose, and we don't know how to. I mean, I'm not saying this is not possible. Like our deterministic analysis. So most of the gap is actually not in the, well, actually it's in both, but even in the deterministic analysis, our deterministic analysis looks at summarizes the alignment between the student kernel and the teacher kernel based on a single number, which is essentially it's not exactly, I mean, you have to be careful, but it's roughly this, in a case like this, it'll be the spectral gap, right? In the gap, but if the kernel has many levels or is decays, then that single number, the biggest gap, doesn't capture the entire behavior. Okay? And so that and that gap we can analyze actually pretty well. But yeah, we know the decomposition, but then we have to figure out. Yeah, so we can write out. We get expressions for these series that represent so we couldn't figure. I mean, okay, I don't know. Maybe you talk later. I'm sure this can be done, but we were not able to do so. Okay. Okay. Where am I? Okay. So now here we show the quadratic gap, but you can ask, is it possible to get even more than a quadratic gap? So first of all, maybe my analysis here, or analysis here even for the linear case was loose, and maybe if Andrea analyzed it, he could show not a quadratic gap, but a quartic gap. Okay. And the second is, even if for this case our analysis was tight, maybe there's a different case, not with spherical data, or maybe with some other activation function or something that will give us something even more than a quadratic gap. Like, can we get a cubic or quartic gap here between the teacher and the student? And it turns out that the answer is no. Okay? So what we can prove is this quadratic gap is the biggest you can get. So in any random feature model, no matter what feature distribution you choose, okay, and what target, okay, the biggest gap you can get is quadratic. So the student error would always be at least the teacher error squared. Okay? And so this shows, I think this to me is even more interesting. It shows like, yes, you can have the student can be better than the teacher, but only to a limited extent. And in fact, these results are even stronger. They don't even have to refer to random feature models. So the lower bound here holds for any feature model. So for any student feature and any teacher features. So even if I choose the student features much, much more cleverly, so if the student teachers really have better inductive bias, or the student features are pre-trained, or whatever you do, no matter what the student features are, no matter what the teacher features are, if you train a linear teacher optimally in its features, and then you train a student teacher by gradient flow on the teacher signal, the biggest gap you can get is quadratic. Okay? And the way we actually prove it is through a generic property. So we prove it more generally. It doesn't even have to be linear. The only thing we rely on is a very weak property, which is the student and the teacher are shrink optimal. So what does shrink optimal mean? Shrink optimal just means that I cannot improve my training objective by scaling down towards 0. Okay? And this is, again, a very weak property. It's satisfied definitely if I'm doing linear learning, or also if I'm doing any type of gradient flow. Right? I always come from below, right? I'm never going to get to, I'm never going to continue optimizing away from 0 if if I already have small error, right? So this is satisfied for also gradient flow. It's satisfied, in fact, for any kind of convex optimization. So if the teacher, if any convex set includes the origin, the teacher is just chosen from this convex set, and the student is also has its own convex set. So both if there's a convex hypothesis classes or convex regularizers, so norms. I wrote here norm, but really it's any convex any convex regularizer. All of these training rules, so minimizing or regularizing a convex set, doing gradient, any type of like gradient flow or mirror descent or something like that, with early stopping, all of them satisfy shrink optimality. So if you do any of those things, you would always have this hit this quadratic limit. And this quadratic limit is interesting because it means that yes, you can have weak to strong generalization, but what you cannot have is the student cannot be perfect without the teacher being perfect, or the student error cannot go to 0 unless the teacher error goes to 0. So if you really want an almighty student that have diminishing error, the teacher also has to have diminishing error. And in particular, if the teacher error is very close to 1, the student error is also very close to 1. So you can only kind of get improvement in the middle, but you cannot get a slightly, a teacher that's just, and it goes a bit back to Renee's question, you can't get a teacher that just has an edge over being completely dumb, right? So a teacher that's just like slightly knows something, and somehow get a student that's a genius. Okay? And this is in contrast to what you get in boosting, right? So in boosting, you exactly do get the situation. As long as you have a weak learner and that is even has any edge, any constant edge over nothing, over being random, over the null, then you can boost the teacher, not the teacher there, sorry, you can boost, you can use it to learn a predictor that's arbitrarily good. So we cannot get this here, okay? Yes?
This relies on the condition that you have to optimally early stop. So, for instance,
so this holds this holds for any early stopping. It doesn't have to be optimal because again, it holds for any shrink optimal student and shrink optimal teacher. And any amount of early stopping would be shrink optimal. You don't have to be to the early stopping.
no, okay. So, but let me rephrase my question. So, for instance, if we regularize, but if we do so in an optimal way, and by optimal way, I mean like we use
this would still hold, because again the condition is very weak. The shrink optimality is very weak. So let me show you the reasoning, and maybe you'll see later. And also, I do want to actually try to finish at least most of my talk. So let me continue a bit. Okay, let me skip. Okay, actually, I should say there's also work for weak to strong that has type of this effect, but the situation there, if you're not familiar with this work, don't worry about it too much. The situation there is very different. Most of the effect of the weak to strong learning is because the teacher is actually overfitting and the student corrects the overfitting by the teacher, and that's much easier to do. Okay, and what I want to emphasize though is this: when I said that this holds very generally for any convex regularizer or convex optimization, the one important property here, we're talking about shrink optimality, so it's shrinking towards zero. So my models have to include the origin. So if we're talking about a convex set, it has to be a convex set that includes the origin, or the convex regularizer has to be towards the origin. So that's why saying norm is maybe more correct. It's only with the regularization towards the origin. If I'm regularizing towards some other point, then as we'll see soon, then you can be arbitrarily good because maybe just that point you're regularizing towards is already perfect. The teacher doesn't have to be, the student doesn't have to be learn anything. Okay, and we'll see that in a second. Okay, so actually what I want to show you is this lower bound, which is super easy to see. And I think it's very insightful to understanding what's going on here. Okay, so this is entirely, we're going to prove this lower bound. This is entirely geometric proof. And so what we're going to plot here, this whiteboard, or not, whatever, the slide board, is the space of all predictors in a geometry that corresponds to the data norm, so to inner products with respect to the data. Okay, so in particular, distances on this whiteboard corresponds to squared errors in between predictors, and so this is the correct predictor. Okay. F star, this is the true target. This is reality, and I'm normalizing it to have to be unit 1 from 0, so this means it's normalized, or if I predict 0, I have an error of 1. Okay, so now I'm going to start by the teacher. So the teacher is maybe somewhere here, okay? So this is a teacher. So the thing is, what I'm claiming is the teacher cannot be there. Why can a teacher not be at that point? Because that teacher is not shrink optimal. Because if I take this teacher down, it actually becomes closer to F star, so this distance is the error, right? The distance between Ft and F star is the error of the teacher. And if I take this down, I actually reduce the error. Okay, so this is exactly what shrink optimality says I cannot do. So this teacher is not shrink optimal. The shrink optimal teachers are only over here. So these teachers, all of these, I cannot improve them just by bringing them down to 0. So my shrink optimality assumption says that the teacher is going to be somewhere over here. The teacher is not going to be unnecessarily far away from the origin. Okay? Okay, so now along this line, these are shrink optimal teachers. As I rotate these lines, the shrink optimal teachers are always going to be below the projection from the teacher. The geometrical location of that point is exactly a sphere between the origin and F star. Okay? So the teachers, shrink optimal teachers, lie somewhere inside here in this sphere. Okay? So this is where the teacher is. So we have some teacher. Let's take this teacher, for example. Okay? So let's take this teacher. This is the error to the teacher. Now the question is, where can the students lie? So again, under the student has to be shrink optimal with respect to the teacher. So that means that the student have to be on a sphere between the origin and the teacher. So this is where the students can be. And now I'm almost done because all I have to say is I want to bound the ratio between the teacher and the best student. So the best student is just a projection of the of the truth to the sphere. So this is the best student, and all I have to do now is bound the ratio between this segment, the length of this segment, and the length of this segment. And this is a simple geometric problem. So I don't know, at least if you're my smart student, you immediately see it through geometry. I had to do this with like writing down the algebra to actually convince myself that it's true. But this is all there is to it. And you write it down, and you get this inequality. OK, but now, so hopefully the proof is clear here. It's a very simple proof. And I think get some intuition for what's going on here. What we have to be careful in is Remy said, this is going to be, we said this is the best teacher, but the best student, but it's not like the student is actually going to be here. Because when a student learns, right, what they see is this point. They have no idea that they have to project this. Okay? So how is learning actually happens, right? So the way actually learning actually happens is, first of all, we train the teacher. So how do we train the teacher? Like, for example, maybe the teacher has some subspace and trains optimally in that subspace, so the teacher ends up here. And now the student comes along, and the student learns. So how's the student going to learn? The student is going to have its own subspace. So maybe, for example, this is the student subspace. And where is it? Why is it not showing? OK, maybe this is the student subspace. Okay? If this is a student subspace, okay, so it means the student has to be lying here. And what the student sees, it sees the teacher signal. It sees its subspace. And the student is going to be the projection of the teacher onto its subspace. So this student, is this a good student or a bad student? Bad student. This is not Marco, right? This is a really bad student. Okay, this student is much worse than a teacher because it's somehow projecting. We all have such students, right? It's kind of projecting to like a completely ridiculous, like bad subspace, right? Okay, so just remember, this is one kind of teacher that has a constraint to a subspace. The type of teachers we're talking, the type of students we're talking about, it's not necessarily just they can project to a subspace. They're also affected by the covariance structure there, which is kind of like regularizing based off a quadratic regularizer with a shape given by the covariance. So the correct way to think about the student is a student looks like something like this, right? A student is a Gaussian or like a quadratic, okay? So if this was the student, like a quadratic like this, what this means is the student tries to find a point that balances this quadratic norm and the distance to the teacher. Okay, which basically corresponds to defining sticking to some sublevel set of this on some sublevel set of this quadratic. It projects the teacher to some sublevel sets of the quadratic. This is if we're doing exact regularization, explicit regularization. That's not what we're doing here. We're doing gradient flow. So gradient flow looks very similar to that. It's actually a bit more extreme. What gradient flow does, this is a gradient flow path. It says first moves to the direction of higher variance. First moves towards. It's trying to get to this point, but the path it's going to get there is not a straight line, or it's a straight line under some other geometry. It's going to first kind of move in towards FT, but in the directions of high variance, so towards here, and then kind of curve towards FT. And we stop with early stopping at some point, maybe you get to this point. Okay, but again, this is a bad teacher. How does a good teacher look like? A good teacher is actually aligned with the target, like has some sense of where should the target be. So this is maybe a good teacher, a good student. And now if we take this good student and project the teacher onto it, now you get into this point. Okay? So this is now the student really is better than the teacher, but it's still the student. What we definitely know for sure, the student is going to be somewhere inside the sphere, and so it's could be better than the teacher like this one, but only quadratically better. Okay? And so now, this is all when the student is around the origin. Okay? If the student is not around the origin, so for example, maybe this is the student. So what does this student correspond to? This is the correspondent not only that prefers certain directions, but also prefers a student point in space. So that would correspond to not using just pre-trained features, but actually fine-tuning a pre-trained model. Right? So you're saying, okay, I already pre-trained to this model. I want to remain close to it under some geometry. Okay? And such a student can be much, much better than the teacher. Right? Because now if I can project to here, I'm well outside the circle. In fact, if I take this pre-trained model very close to F star, then the student can be arbitrarily close to F star, right? Because the student doesn't even have to learn, it already knows everything. Okay, so, and this is what I mean by the fact that the origin, the inclusion of the origin, or regularizing through the origin, is crucial for this lower bound. What? That's a postdoc, yeah. Okay, so so let's summarize. So I think that what's interesting is to think of different ways of the student being better than the teacher, and for these ways, is there a limit? Can the student be better than the teacher, and by how much? Is there a limit to that? Okay. So we talked first of all about test time compute and self-play, and in those cases, it's pretty clear that you can have arbitrarily high gains. The student can really be much arbitrarily better than the teacher. Okay. Then the other way we said the student could be better than the teacher is if it has better inductive bias, better pre-training. Like if the student already knows Chinese, if the student already knows stuff, if the student already knows the relevant features. And now we see that it's actually, we have to be a bit more careful with that in terms of how much better can the student be than the teacher. If the way that the student uses this extra information is just to choose features, but it's going to train from the origin, okay, so just chooses the direction, then it can be better than the teacher, but only quadratically so. If what it does is fine-tuning, like initializing to the pre-trained model and optimizing from there, then it can be arbitrarily better. Okay? The other way that student can be better than the teacher is just by having a bigger brain. Okay? And that's kind of the setting we started with. And what we saw is even in that case, okay, even if the student does not have any more inductive bias, they're kind of the same, just bigger. It can be bigger. It can be better, but with the only quadratically so. Now I want to emphasize that. Okay, and then there's actually another way that we didn't talk about in this talk, but another way for the teacher to be better than the student. Sorry, for the student to be better than the teacher is if the teacher does something stupid, like for example overfits, or stops too early, stops too late, like adds, the teacher artificially adds noise. In all those cases, again, the overfitting actually chooses the bad regularization parameters, maybe the easiest way to think, and that's actually what implicitly happens in some of the other analysis. And the main reason I'm mentioning this is you have to be very careful in analysis. When we started working on this, we had all kinds of models where the teacher is much, much better than the student, and then we realized it's all just because the way we're setting up the problem, we're forcing the teacher to use bad parameters, bad regularization parameters. Okay, so, okay. Now, going back to this quadratic limit, I emphasize this quadratic limit, but this quadratic limit really only applies, or at least we can only prove it, when for convex problems. It doesn't have to be linear. The important thing is convex. For convex problems, and we're minimizing the squared loss. Okay? I think it's an interesting question, to me, completely open. How strong can the weak to strong generalization be if either you're looking at non-convex classes? So for example, take back our two-layer network, but actually, I'm sorry, Andrea, don't use random features, but just actually train both layers, right? So if you actually train both layers, we can still, the question is completely well defined. There's no more inductive bias here. Again, it's just, the teacher is a small two-layer neural net, the student is a big two-layer neural net. You train the teacher optimally, you train the student with the gradient flow and all the way to the teacher. How much better can the student be better than the teacher? And our lower bound does not apply to that because now it's a non-convex optimization problem. And the second is that our lower bounds only apply for squared loss. This whole geometric picture is very specific to the squared loss. And if you use for classification problems with a log loss, I actually don't know what happens. I mean, whether the student can be, it's clear it can be quadratically better because you can kind of get squared loss type behavior, but it might be much, you might be able to get better, it might be a limit or no limit, I don't know. Okay, let me just finish here. And again, just to summarize, we looked at weak to strong generalizations, where our emphasis would really try to isolate specifically the benefit of just having a bigger model, not other types of benefits. We looked at the simplest possible model we can think of, which is random feature models. We saw you could get weak to strong generalization, but maybe even more importantly, we saw limits to weak to strong generalization that apply very broadly, not just in random feature models, but also in many other type of models. And I'll be happy to take any more questions or deflect them all to Marco. Okay, thank you.